All right, so are there any questions from last time?
Wait, sorry, I'll close the door.
Yeah, that makes sense. Did you have questions from last time? Last time was a little bit of a hodgepodge of different subjects, but I think they're all kind of important. So there was sort of deployability of contextual bandits and general use. There was the non-stationary policy evaluation, and then there was sample complexity for reinforcement learning.
I mean, why did you say in the beginning of the course that CDP have supervision?
CDP has supervision.
Yeah.
I don't recall saying that.
I mean, so in the beginning you showed us these like circles, like supervision, reinforcement, exploration.
Yeah.
Place CDP in the intersection of all three.
Ooh.
That's what did you say?
Contextual decision process.
I think the claim was that there's a sample complexity bound for CDP, not that it is supervision. Well, I think we can go, so at the end of the class, I was planning to kind of revisit some of those slides, and then we can reinterpret our understanding of things.
Okay.
Okay, so today's lecture is based upon an ICML tutorial that we did in 2015 with Hal Daum. This is about learning to search and how you use it for joint prediction and the relationship with reinforcement learning. So this particular the tutorial was essentially longer than an hour and 10 minutes. So my plan is to kind of go at a reasonable pace. You should interrupt me, and if we go over, then we'll just continue next lecture. I think that everything together kind of, I guess, I've kind of felt like this class is running over things relatively fast. And so I'm going to go relatively slow here so that hopefully you can understand it better. Okay, so where are we going? Right. Okay, so we're trying to do. I think often it's been called structure prediction, but I'm going to call it joint prediction because I'm not going to assume that a particular. The setting is you want to predict a bunch of things together, and often in the past, like in the CRF days or whatever, people assumed some structure over those predictions. But I think the assumption of structure there was often for computational convenience, while here, I think the fundamental problem is really the joint prediction problem. You have a joint set you want to predict, and it's that joint set which kind of has a well-defined notion of success or failure. Right. So a simple example of this is sequence labeling. So the monster ate the sandwich, had determiner, noun, verb, determiner, noun. There's also like entity recognition. Is that a person or a place? And then there's other variations of this which happen with DNA, trying to find splice sites or other important pieces in the DNA.
So trees don't fall under this category.
Trees would not fall under this category. This is just sequence labeling.
No.
But we will be talking about trees do fall in the category of joint prediction. So I'm talking about joint prediction. I'm giving you examples involving sequence labeling.
Yeah, no. That's what I said. It doesn't fall under the category of joint prediction. It is structure.
I would say it does fall under the category of joint prediction. And in fact, we have worked on dependency parsing.
But it's structure. So here every label is possible, independent of the others, but there is dependencies in the decisions between them.
It's not actually true. Some conditioned on some of the past predictions, you may some future predictions may not be allowed, even in sequence labeling.
Yeah, in any other, right.
I'm not sure. Why do you say joint prediction? Like joint over what?
So what I mean is you have some space which is kind of defined in a combinatorial fashion. So you have a set. So it's not like you're predicting a label. It's like you're predicting a bunch of labels. And
joined over even like all those labels together.
Yes.
So sequence meaning like these.
Yeah. So the key difference in my mind is that the computational complexity of treating every sequence as a label is totally overwhelming because you'd be choosing amongst an enormously large number of possible labels.
So why are you making a distinction of structured and joint? You don't like structured, but you like joint.
I think that what's being addressed here is joint prediction. I think structured learning is it's often overloaded with assuming a structure about how the world works. And when you say structured prediction to people, I think often they think of CRFs.
Mm-hmm.
And so there's an assumption about the approach that you're using to solve the problem, which is not true here.
Mm-hmm.
So I think that the problem being addressed is joint prediction. It is applied in settings where often there is structure in the past. But that structure is sort of, I mean, to some extent it may be real, and to the extent that it is real, that's important. But to some extent, I think it's kind of a computational convenience. I don't think people actually believe the conditional independent structure that CRFs imply. Who knows what a conditional random field is? Okay, just a few people. Okay, so I think they're now out of favor.
No, you can put them on the neural network.
Yeah, so nowadays people do neural networks instead, but
no, you put them on top of.
Okay, you put them on top of a neural network.
That's the best parsing results. You put the CRF on top of it.
Not anymore.
Oh, well. Yesterday.
Okay, so yeah, there's dependency parsing. Which elements of a sentence depend upon which other elements? What you can think of as joint prediction. There's sort of bipartite matching problems. Which words correspond to which other words in another language. There's machine translation, which you can think of this way. There's image segmentation, which of the things found by a LiDAR or a sonar are part of a simple object, or what kind of objects are you getting bounces off of? And so there's go ahead.
This is still allowing for some of the things you're predicting to be highly dependent on each other, right?
Yeah, so we definitely, it's critical that we allow predictions to be very dependent upon other predictions or on information carried over from other parts of the space. Yeah. Okay, so protein secondary structure prediction. So the primary structure is the sequence of amino acids in the protein. The secondary structure is how they fold together. Okay, so there's several approaches people take to solve these problems. The simplest approach, which I think is often the first pass approach in any individual problem, is to just say, oh, I'll just predict everything independently, right? And if you do that for a lot of these problems, you get some performance. Sometimes it's good-ish, but you're kind of missing some details. You don't get the best performance that you can. And furthermore, the predictions that you get tend to be rather disjoint. So if you look at this LiDAR image, you might classify some parts of the object as tree and some parts as wall, back and forth in no kind of coherent pattern, just because the local structure isn't very good at carrying information. All right, so it's also kind of a shared parameters approach. I think this is currently the most popular approach. This is where you have some sort of representation which integrates a bunch of information, and then you have a bunch of output predictions coming on top of that, right? So this would be kind of the neural network approach to a large extent. So you have some sort of shared representation, which is then used to output individual predictions.
In multitask, you generally have like auxiliary tasks that you're also.
What's that?
I mean, in multitask setting, you generally have these auxiliary tasks. For example, you have an embedding which is used to do segmentation, also used to predict something else.
Could be, but
Is that what you mean?
I think there are many variations. That would be one variation. The thing which I think is fairly important to note is that the multitask learning approach is still kind of doing independent optimization. It's just that with a shared representation, and they can benefit from that shared representation, but they're still kind of optimizing each thing independently. Okay, and then there's the CRF approach, which is you assume that the world obeys a Markov random field or conditional random field or hidden Markov model, one of these variations, and then you optimize the representation under that assumption, right? And then the fourth approach, which I think is fairly common, is you just kind of have a handcrafted solution. So I think for machine translation for a long time, and maybe even still to a significant extent, uses some sort of handcrafted solution, which is it's a very important problem. So when it's a very important problem, people will handcraft things. They will do whatever works, and maybe there's elements of these things which are mixed together. Maybe it's a CRF on top of a neural network, but there's a lot of kind of handcrafting about the solution. So it's not easily transferred to a new problem. Okay, so these are sort of the standard things. This is not what we're really going to talk about. We're going to talk instead about a different approach. But I want to first think about what predicting independently means. So maybe you have, there's my mouse. You have some features of nearby voxels, and then you want to predict a class. Is it part of a tree, a pole, or a wall, or the ground? Okay, so this is very simple to implement. It's typically very efficient, and it does not capture correlations between adjacent predictions very well. It does not really optimize a joint loss in any kind of coherent sense. Okay, so it's kind of a disadvantage. You can predict with a kind of a multitask approach. So then you have your features going to some hidden representation, which is what neural networks often are used for. And then out of that, you have individual predictions. You share the hidden representation that gives you most of the advantages of predicting independently, but you can capture correlations in kind of an implicit fashion through the shared representation.
So what do you mean by this? So this is like a recurrent neural network or something? So you have some kind of like, you have your recurrence with the hidden state, but the prediction is actually done on top of it independently from each of the hidden states.
So a recurrent neural network is actually something in between what I would think of as a multitask bias and the learning to search stuff that I'm going to talk about. With a recurrent neural network, typically you're still not optimizing the global loss, but the internal state is changing as you make predictions, and that's fairly powerful in giving good results. So I think we're working with an imperfect classification because methodology is changing relatively rapidly.
I mean, why do you say RNN don't minimize the global loss?
I mean, it depends on the RNN. Usually they do.
Typically, RNNs are optimizing some sort of log loss thing, cross entropy or whatever.
Yeah, I mean, log likelihood, but
on the token level.
Yeah, that's right. But because of the history that they're carrying, they're actually doing the global loss.
I'm not claiming that they can't. No, that's not the global loss. Typically, the global loss is something like blue score or whatever.
Oh, okay.
Right?
Yeah, fair enough.
Or you can have the global loss. It will be the product of the probability of the center.
Yeah, and you can model that with an RNN, but not with like a not with like CRF or HML.
So I think that if you're optimizing log loss, you are really optimizing a proxy loss for the true loss. I think the true loss is never really log loss, except in the case when you happen to be doing coding length for compression.
I mean, if you're doing language modeling, then log loss is your.
Yeah, because that's the complexity.
Yeah, I agree that language people are very hung up on log loss. I don't think that log loss actually expresses the true problem they're trying to solve in language.
Oh, yeah.
Right. So I have friends who are working on question answering systems for tech support. Right. And I don't think log loss is what they care about.
The actual
what they care about is, do they manage to get across a reasonable answer in a semi-automated fashion?
Yeah, but those things are very hard to sometimes objectify.
Yeah. But what we're trying to get, it may be very hard to objectify, but you can actually observe success or failure in an interaction. Right. And that gives you some sort of implicit true loss function you care about. And now you kind of have a choice in what you're optimizing. You can try to optimize some kind of proxy loss you choose because it's convenient, or you can try to optimize that implicitly defined loss function for whatever problem you really care about. And I guess to a large extent, I've been talking about how you can make the second approach be tractable throughout several different lectures here.
What would be an example of this, if the same image thing?
Yeah, so you could imagine having a neural network which looks at the image using some sort of convolution operator. It builds up a representation of the image internally, and then you have a bunch of outputs coming off that internal representation to predict what's in each individual voxel. Right?
Yeah, okay.
Okay, so learning for these things can be somewhat hard. It's kind of, I think for this particular problem, people have not tried to solve that problem. Not tried to solve by using that combined neural network approach that I just mentioned. It still does not optimize the joint loss. It optimizes kind of an individual log loss for each output.
So I have a question. So what
Yeah.
does it mean, like when you say joint loss? Does it mean that you have a predicted sequence and a sequence of structure, and then you have a ground truth structure, and there is some loss which quantizes like how much these two differ, right?
Yes.
And when the Benzer says like log loss, it means like, okay, at each step of my prediction, let's say I'm predicting words, I'm just saying, oh, this word doesn't match, or this word has a prediction probability of p, so I'll take log p loss. Like that's the thing we say, like, and the way we decompose this loss, like the difference between two sentences or two sequences or structures, the way we decompose into things is what we are talking here, right?
Yeah, I think the question is,
Yeah. So here we talk about breaking them into saying that each decision in the structure is independent.
yeah. So you're kind of saying the loss of each individual thing is independent, but because there's this shared structure underneath, I think
Yes.
often this approach does work better than the independent prediction approach.
Yeah. So I don't understand the difference in previous one and this one. So this also.
So when I say independent prediction, what I mean is there's some function at scoring time. You have some function which gets applied to the input, and then there's an output. And then you get applied to a different piece of the input, and you get a different output. And so it's just you have a function which gets applied to a subset of the input and gives you an output for that subset, right?
Yeah.
When I say something with a shared representation, multitask bias, what I'm saying is there's a function which is used to kind of summarize everything in the set, and then you have outputs coming from that summarization.
Oh my God. Okay. Yeah.
Right.
Makes sense.
Okay. It's also graphical models. So graphical models are actually, I think, the first approach people use with this particular data set. You can say, look, there's some potential for a classification to change for adjacent voxels, and you want to kind of learn that potential function as a function of local features, and then you can use belief propagation approaches. So we're getting way too complex. So when I say belief propagation, what I mean is just that given the evidence that you have in one corner of the screen, you don't necessarily know what the prediction should be because you need to incorporate the information from adjacent elements. But those need to incorporate information from adjacent elements. But those need to keep incorporating information from adjacent elements and so forth, right? So what you do in belief propagation is you can prove under strong conditional independence assumptions that you can do, it's called a forward-backward algorithm. You can integrate the information here with information there, with information there, and so forth, and to build up that information as you propagate down a chain, and then you can propagate backwards to incorporate into the chain in the prediction at the beginning. And it's complex. I shouldn't try.
So would an example just be like Viterbi?
Yeah, Viterbi is doing this. Exactly. Okay, so you kind of guarantee to get consistent outputs. You can capture correlations explicitly. The conditional independence assumptions that you make are actually quite strong, and they're often wrong in practice. And it's also kind of computationally intractable in the sense that if you have a chain, it works great. So if you just have a sequence, it works great. But if you have a graph structure like this, where you have a 2D field, then the computational complexity of an exact answer becomes intractable, and then you very easily start going into approximation land, and then things start to become hard. Okay, so now let's just think about what the problem is at a high level. So you have some input, which is the features x. You have some true label, y. You have some outputs, which are in the same space as the labels. You have some predicted output, y hat. And then we have some loss function between y and y hat. So for machine translation, one of the things I pay attention to is BLEU score, which I don't actually know the exact definition of, but I believe it involves things involving kind of did you get the individual words right? Did you get the bigrams right, the trigrams, the quadgrams, and some sort of combination of these? So it's a kind of a non-trivially complex loss function, which is automated. It's imperfect compared to what a human might judge, but it's probably a lot better than the simplistic things you might otherwise consider. Okay, so then you have data, and we're going to imagine, just as in a supervised learning setting, that you have an x and a y, which are coming from a distribution D independently. But now y is this kind of complex thing, which is like kind of like a prediction every location in a sequence, or a parse tree for dependency parsing, or things like that. Okay, so the input might be I can, a can. The truth might be pronoun, what's MD? Modal? Modifier. Verb, determiner, noun. Your possible outputs is a space. You could have many different predictions at different locations. Your goal is to find some H which predicts that y of x based upon n samples that are drawn independently according to D. And you want to minimize, you want to minimize the loss, right? So this is standard supervised learning, except for the fact that y of x is just a complex object. Okay, so now, because it's a complex object, the output space is very big. You can't really do a search through it. You can't enumerate all the possibilities. That would kill your computer. So you need some way to decompose things. And often there's kind of a natural decomposition which exists in individual problems. Maybe there's prediction by word or by voxel or things like that. And the other thing is that the loss function may be relatively complex. So maybe you want the edit distance, or maybe you're doing intersection over union, or maybe doing the BLEU score, or maybe there's a lot of other possibilities which are kind of, they're relatively easy to compute given the y hat and the y, but there's a fair amount of structure in them, so that it's hard to understand the incremental impact on their value given a commitment of a partial prediction. Okay, so when you can decompose the y, there's often an ordering which you can naturally impose. So you can go from the beginning to the end, or maybe you can go from the beginning to the end and then back to the beginning, or maybe you can go from the end to the beginning. There's these kind of choices which are available and which are relatively natural given the ability to decompose the structure. I guess often there's an adjacency structure in the joint predictions that you're making, and so it's very natural to kind of try to obey the adjacency structure as you go through the process of making a sequence of predictions. Okay, so this is not always obvious, but there's some ways to handle that to some extent. Okay, so now what we're going to do is we're going to think about making a sequence of predictions. So maybe we want to predict the part of speech for the first word, and then the second word, and then the third word, and so forth, right? And so we can think of this as a search space where the possible outputs of a node are the different types of speech, and the space has a depth equal to the number of predictions that we want to make, right? So the edges are part of speech for an individual word here, and the nodes are where the learning happens, where you need to make a prediction. You need to predict at each node which way to go. So
does the amount of choices change when you go to the next stage, or it's like do you roll out or the wrong like options?
Yeah. So in general, the number of choices may be constrained in arbitrary ways by your history.
I'm saying it's like if you have a action, like if you have a choice where the first one is wrong, and everything else were correct, you won't choose it because you will step first in the first stage, choose the problem, and then you will, because the correct option didn't have, not the correct, almost correct option didn't have this first one correctly, you won't consider it in time, like anymore. Did you get it?
So I haven't defined how we're going to go through the search space yet. I'm just saying that there is a search space so far. So there is a search space, and then later we'll talk about how we're going to go through it. But for now, there is a search space. When you get to the end of the search space, you have a loss that's defined. And the individual nodes in the search space is where your learning happens. You need to learn which way to step. And now I think you can probably start to see how this is related to reinforcement learning. Because in reinforcement learning, you're making a sequence of actions, and it's the sum of the rewards that you get which matters. So you only really know that at the end. Maybe your reward entirely comes at the end in reinforcement learning sometimes. And your decisions are being made at the points where you have to choose amongst actions. And so this is one of the reasons why this approach, I think, interests me, is because it is addressing reinforcement learning at the same time to some extent. Okay.
If we think about reinforcement learning, should we have some state in mind? Like, what is the state here? Is like the whole
Yeah, so you have at least a partial prediction around, and there's sort of the information encoded in the features for previous predictions, which may be important in a state sense.
Okay.
Okay.
You don't have like, I mean, so this is like, so learning here is fully supervised in a sense.
Here we can be fully supervised, but it's just a small step to be not fully supervised, because the structure of what we're trying to learn easily incorporates that. Okay, so at the end you have this output, which is your loss, right? So you can descend through the search space, you reach the end, and now you have a complete prediction. You can compare with your complete label, and you get a loss. All right, so now we're going to think about a policy, and we'll call it a policy in the same sense with reinforcement learning. So you have some input, which is your features. Maybe you want to add the time step to the features as well. You have some partial trajectory, which is you have your previous predictions that you've made. Those can be a part of your feature space as well. And now you want to make a prediction about the next thing that you're optimizing, or the next step to take, next in the sequence. Okay, so compared to reinforcement learning a little bit, we have an observation, we take an action, observation, action, and so forth. At the end, there's a loss. So this is a lot like reinforcement learning. So the policy is essentially a classifier. It's choosing amongst a discrete set of actions. Our goal is to minimize the expected loss. So this is, again, quite a bit like reinforcement learning. And the key difference is that we're in a supervised setting, right? So we can, in reinforcement learning, you can only, what I think of as a true reinforcement learning setting, you can only ever take one action from a given observation. But here, we can actually say, oh, what would have happened if we had taken a different action too, and then rolled things out?
Why would you say that in reinforcement learning you can take only one action?
I mean, in the general reinforcement learning setting, what I think of as general reinforcement learning setting, you see some features, you take an action, maybe see a reward, and you just keep continuing to the end of an episode.
Action, but you can only observe one.
So you may only ever observe that setting of the features once. So the state which you're trying to predict based upon, the state is a bad word. The features you're trying to predict based upon
only see one.
may only be seen once in the real world.
I mean, you can, yeah. Like
if you're running in the simulator, this is not true, of course.
I mean, yeah.
But in the real world, I think you really just never get back to exactly the same observation.
This might be kind of orthogonal what the point is here, but would there ever be a case where you would want to like look at the like partial loss? I don't know if you can say that, but like at somewhere before you end the sequence, like you take a look at how you're doing and kind of reward or reflect or update based on that. I mean, that's not really related to which learning method, but
Yeah.
Early updates.
What's that?
Early updates.
Yeah. Yeah. So there's certainly settings where you'd want to do that. It's kind of tricky. Well, let's discuss that a little bit more in a moment. Okay.
I mean, you can have a loss function which decomposes over the structure or over
You
the
can.
trajectory. I mean,
Yeah.
For example, roboticists, they have these algorithms called CHOMP and these like trajectory optimization algorithms where the loss function actually decomposes and makes the optimization easier.
Yeah. So when the loss function happens to decompose, that can make things easier. It's true.
Is there any learning problem where you can't? So what's the learning problem you can't think about in this kind of like sequential decision process?
Well, certainly a lot of one-shot things where thinking of it as a sequence of length one is not very helpful.
Well, yeah. Well, I mean, yeah, the generative way, like okay, sequence of length one. That's a classification
So
and stuff like that.
ImageNet is an example of something where it's kind of a one-shot thing. You get the image in, you get the prediction out.
Okay, but except so of course, so except the things that like structured, but you can't think of them in sequence. Just that's not applied. Just trying to think about it. Can't find an example.
I mean, I mean, that thing must have some kind of an atom. You just break atom by atom, right? If it's an image, it's like generate image, it's a tree node by node and edges.
So I think
the world to atoms.
it can certainly be the case that there are problems where you really want to summarize a lot of information before you make a prediction. Right. What's that?
It can still be a sequence.
Yeah, but it's kind of a funny sequence where you do a bunch of stuff which is not on the final output, and then you do stuff which is on the final output.
This is like latent variable.
What's that?
This is latent variable learning in a sense.
Yeah.
You predict the latent variables and then you spit out the output.
Yeah, I agree.
Yeah, anything that humans do is also sequential decision.
I don't know.
AI problems are
Supposed to multitask.
If only I had 3 hands, I could do 3 times as much. Okay, so let's think about a going from labeled data to a reference policy. So when you have labeled data, you can evaluate the loss at the end. But often what we want, if you just start with an arbitrary policy, the odds that you get a good solution are pretty low. And that solution may, it may be very hard to improve that to reach a high quality solution. But because you have labeled data around, for many problems, it's possible to divine from the labeled information what is a good policy. And when I say policy, I mean something stronger than just the labels, because I mean, given any partial prediction, what is a good next step to continue that? Right? So if all your predictions so far are good, then the next one should be according to your label. So it's easy. But if you make errors in your predictions so far, then you want to be able to use your label information to drive towards the best possible solution conditioned on the errors that have been made so far. Is this clear? So I think a critical question is, why do you want this? And the answer is essentially that you're switching through a combinatorially large space. So you want an edge to go through that combinatorially large space. That edge is your labeled information. And now we just need something a little bit stronger than labeled information, so that when we deviate from the golden track, we want to know how to get back onto the golden track to minimum loss, or to get as close to it as possible. And then something relatively magical will happen. Okay, so the minimum achievable loss is this minimum over this incredibly large set. The optimal action given any partial prediction is the argmin of this, right? So that for the next step in that sequence, right? So you have some partial prediction, A1 through AT minus 1, and now you want to figure out what to do for AT through whatever. So we want to have a reference policy which tells us which next action to take, which is according to the argmin over AT of this minimization process. Okay, so it seems a little bit complex, and there often is some creativity which goes into the definition of a reference policy given label information. So for things like, for the speech technique, you might use handing loss, and then this is trivial. Just the next AT is equal to the label. But if you're doing named entity recognition and you have multiple words in an entity, maybe you can't correct immediately. Maybe you have to do something slightly more complex. And when you're doing dependency parsing, I think it becomes actually quite complex. You want to start thinking about what is the best. Given that you've given a bad partial parse, how do you actually complete that to give you the best possible solutions you can get?
So this is first of all that you're supervised reference policy.
Yeah. So here we're supervised.
And second of all, that you have a partial credit at the end. If you don't have partial credit, you're already dead.
It's not partial credit. Oh yes. That's right. So we're assuming that the loss is not just 0, 1 at the end. I mean, if that's true, then you're dead, as you say.
I mean, the reference policy has to be complete, right? It should.
It needs to be complete for the states you actually encounter, for the partial predictions you actually encounter.
It should be able to produce an action for any state.
Yeah.
Because otherwise, you can just simply like have a dependency tree, you just read it as a sequence and then just follow that.
Yeah. Okay. So the optimal policy is the one which always selects the optimal action. Often you can't actually get to an optimal policy. Often you can only kind of approximately optimize this, and then we call it a reference policy. So you can also imagine using this in a true reinforcement-oriented situation, where the reference policy will be, okay, now a human does it, and then the human can go and finish things off from wherever the robot got to, or something like that. Okay, so where are we at? We have training data. We have an output space. We have a loss function. We have some decomposition into observations and actions, and we have a reference policy. And now, I did set this up in advance, but
You can work on reference policy that is only partial. So let's say you have some kind of latent decisions along the way, but your reference policy is only over the observed.
yeah, there actually is. So Hal had a paper on unsupervised CERN a while ago, where you were essentially making decisions which are arbitrary, and their only function was to carry information for future decisions. And now there wasn't any good reference policy, so you just started with a random one. And then you let the optimization kind of drive the semantics of the process.
And it
ended up working fairly well.
And a random reference policy is as good as no reference policy.
I mean, a reference policy is kind of required to use the algorithms I'm going to talk about in a moment. So in the sense that you need to have something to fill into a slot, you need a random policy is good. Much better than having nothing to fill in.
So can you go back a slide, I guess?
Yeah.
I'm a bit, so what would be the difference between giving, what is the conceptual difference, I guess, between the label data and the reference policy? Like, what do you add, or?
So the reference policy tells you, given any partial prediction, what the next step should be.
Right. And so the label data might not have examples for certain partial trajectories. Is that kind of?
In particular, the label data implicitly defines what to do next, conditioned on you making a correct prediction at every previous step. It doesn't really tell you what to do next if you've made mistakes at previous steps.
What's the difference between an optimal policy and a reference policy? In sense, like we can use the reference policy at the beginning and get to the minimum loss giving structure, right?
So the reference policy, because it's label dependent, in general, it's only going to be available at test time. Or sorry, at training time. At training time.
Training.
It would be useful.
It'd be really useful at test time.
State of the art.
Yeah. So
When you say we want to start training, and to start training we need to have a reference policy in hand,
yeah.
like whatever we are going to do. So when we can learn that from the training data, like why can't we use it? Because it's complete, right? It can give me action for any state, any observation. So I can use it in the test time also, right?
So we're typically using the label and defining the reference policy. And so at test time, when you don't have a label information available, you can't even evaluate the reference policy.
But it also gives you prediction for the observations you didn't see, right?
For the observations, it gives you predictions about which action to take. The observations it does not predict. So the observations.
Like even an observation that doesn't occur in the training set, it also gives you the action, the sequence of actions to take, right?
Yeah, so we need to distinguish. Observation is more complex than just the predictions that have been made previously. Our observation is also the features, right? So we have both features and previous predictions, which are going into our complete observation space for making the next prediction.
I mean, I think what Ashadeep is not getting is that you need the label to compute the action. You cannot. You need the label in the reference policy to get the action.
That's right.
So you don't have the label at test time, so you cannot even compute the reference policy.
So what label do we mean?
Like you need the dependency tree, you need the goal dependency tree, for example, to compute the reference policy.
Oh, okay. Okay.
And also, also the algorithm, I think, John, is going to outperforms reference policy.
Yeah, so the goal is definitely to outperform the
Yeah.
reference. Well,
Yeah.
is that reference policy is the optimal policy, then you can't really outperform it. But sometimes you actually do have a reference policy which is bad, and then you want to be able to outperform it by potentially a lot.
Okay, I think the last paper was claiming that at least it's as good as the reference policy.
When people say as good in theory, what they mean is no more than epsilon worse.
Okay.
It's a little bit conceited. Okay, so I showed you Super Mario Brothers earlier in the first lecture, and I don't think I have it. Let me pull it up real quick. Let's go here. This one. Let's go. Ooh, didn't show you. Interesting.
I didn't see any Mario.
Okay, let me show you then. This one. So these are some videos that Stefan Ross made back when he's at Carnegie Mellon. And let's see this. So let's see if this works. Okay, so these are experts trying to do Super Mario Brothers in some sort of hacked version, and they're reasonably good. So the obvious thing to do is to try to imitate the expert, right? And if you try to imitate the expert, I don't know if you guys can see that. Can you see that at all? Okay.
Yeah.
If you try to imitate the expert, then things get stuck, right? So it gets stuck against the pipe or whatever.
When you say imitate, you mean do behavior cloning?
Just predict what the expert would do given any given situation, right?
So it's Emily.
Yeah.
Okay.
Maximum likelihood type approach. Okay, so right, so think about collecting a bunch of trajectories from experts. I call it the reference policy. We can just store a data set, and now you can try to predict the label given by the expert, given the observation, and then you can just let it play, and you see that things go rather wrong, right? Okay, so another question is kind of what's going wrong. Basically, the expert is smart enough to not get stuck. The learning algorithm makes bad predictions, and then it doesn't know how to unstick itself. It doesn't know how to deal with being in a bad situation, because the expert was never in that situation. This is like a cascading failure problem where the first bad move that the learn policy makes puts it into a situation where it's never observed what to do, and now it doesn't know what to do, so it's just kind of confused, and it just makes a bunch of bad mistakes after that.
This is the type of it's a covariate failure, covariate shift.
Yeah, it's a covariate shift-like issue because you never observe the failure mode, and so you don't know what to do. So the classifier doesn't learn to recover from its own errors.
So this is still reference policy, right?
So we're using the reference policy here to define, we're using an expert as in a reference policy rather than an explicitly defined one to create a data set, and then we predict what the expert would do in any given situation.
So I guess, is this different than using labeled data? Because I guess we're running into the same problem where we don't know how to predict what to do in this like, never mind. I mean, probably a little too.
It is a little bit different. So here we're leaning a little bit into the reinforcement learning view of things. So in the reinforcement learning setting, the reference policy maybe not be something which is computable. Maybe it's just something which is, we can say, oh, here, you as a human go solve this problem, right? But I think that I'm hoping that the relationship is close enough that you can kind of see that this also applies when you're in the labeled setting. So in the labeled setting, if you just learn to mimic the labels with maximum likelihood estimator, if you never learn to deal with the kinds of mistakes that your algorithm makes, that can cause your algorithm to perform rather poorly at test time.
But this is a bit different than a reference policy. The reference policy is like, I'm doing learning now, I made a mistake, but I know what's the optimal next steps to make in order to reach the best score that I can still with. Here, you can get stuck, and you will still be stuck. You will still be against the pipe.
Well, when I showed that video, when I was getting stuck, that was really a test time evaluation.
Yeah, but
I mean, reference policy will tell you how to recover from that.
This in dependency policy, I can build the reference policy from the supervised example. How can I build the reference policy in Supervised?
We're really, so in Super Mario, we're not trying to build a reference policy. We're using a human as a reference policy.
So a human will show how to do.
Yeah, a human was.
But it's not a perfect reference policy. It's not
perfect.
An oracle.
It's not a perfect reference policy, but it is a reference policy. It avoids the severe failure modes. It may not optimize perfectly.
Mm-hmm.
I mean, how is that?
So a reference policy may be imperfect in general.
How will it avoid the severe failure mode?
Well, I think a human typically knows how to jump over things and whatever.
Oh, okay.
Right. So.
I mean, how does that even scale? Like, you have a human which will.
I think this is like a thought experiment here, and I think you're taking it way too literally. Okay, so.
Okay, well, never mind.
Do you have another question?
No, it's okay.
Okay. Okay. Okay. So you get stuck. Classifier does not learn to recover. It's kind of bad. So then you can try to do something which is more like imitation learning. The idea here is that you first do what you just did, and then you collect new trajectories. So you have a human. So you have the algorithm control what the system is doing, but then you have a human constantly trying to correct that, which I think is very frustrating for a human. But you do get the kind of information you need to start learning how to correct from bad situations. So when a car is busy running off the road, they'll be busy trying to steer into the middle of the road. And then you can just aggregate your data sets, and then you can train again. So you get a bunch of steers into the middle of the road here. You train again, and you can just keep doing that over and over again, and get a better and better solution. Okay, so this is a way for the learning algorithm to learn to cope with its own mistakes, given kind of supervisory reference policy. Okay, and this is an algorithm. This is called the Dagger algorithm for data set aggregation. That's useful, but this is still not the best possible algorithm. And it's important to kind of understand why. So you can prove some things about it. Okay, so what goes wrong here? Is kind of an issue with credit. You don't have a good sense. So there may be several actions available, and maybe one of them is the best action, and maybe one of them is a terrible action, and in between you have in between levels of badness. And the policy that you're learning may not be able to always choose the best action for various reasons. Maybe it doesn't have the set complexity required to exploit the best action, because getting that optimal reward may require some very complex things later. Or maybe the representation just doesn't allow you to make the right action given in the context of all the other actions you need to also optimize. So there's no good notion of of how much better something is or how much worse something is. There's no partial credit. You have to kind of have a single answer about what the right action is when you go back to this kind of approach. Okay, so we want to try to get at what is a partial credit approach. So I've already defined cost-sensitive classification for you guys, but I'm just going to go through that again. So you have a classifier, which given features predicts one of several classes, one of k classes. In multi-class classification, you're just trying to minimize your error rate. But in cost-sensitive classification, you're trying to minimize the expected cost of the chosen action. And so this is more expressive than multi-class. In multi-class, you could say, oh, the cost of every wrong action is 1 and the cost of the right action is 0. But here we can have different costs for different actions, which allows us to do partial credit. Okay, so now, now we're going to think about another algorithm called Aggravate. This is also from Stefan Ross and Drew Bagnall. And the idea here is that you let the learned policy drive for some number of time steps to reach some observation, and then for each possible action, you're going to consider deviations. So maybe your initial policy is the red one, and then you choose some time step, and you say, okay, I'm going to consider the deviations from this policy here. So there's a set of possible deviations, and then for each action, you take that action, and then you let the reference policy drive after that. This is something where the robot controls, the computer controls things initially, and then a human takes over after that deviation step happens. Okay, and then you record the loss that you observe at the end, or the reward, if we're in a reward basis.
I mean, here you have the second assumption, which is kind of not an RL setting, right? We're checking for every action A from the original.
Yeah. So that's right. And there'll be a fix for that if we want to do reinforcement learning, because essentially we can randomize the action that's taken instead of taking every action. Okay, so the reference policy completes. Maybe that's a human, or maybe it's something derived from labels, and then you get some loss associated with that. And you can do that for each of the individual actions, and then that will give you some sense of how. It gives you a way to do credit assignment. Essentially, it tells you, given where I am, what is the value of taking this action versus that action versus that action. Okay, so then you can create a cost-sensitive example. So you can say, given the observation which is available at this point, the cost associated with action 1 is what you get when you deviate according to action 1, and then you roll out with your reference policy.
This is relatively high sample complexity. I mean, you have to take entire trajectory of all the actions in order to get one update.
It's certainly, yeah, I think it's correct in some ways, and that can bite hard at times, but we'll find that how to describe this. I think it's actually hard to systematically prove you can do much better. Because if you look at the kinds of reinforcement learning guarantees that we know, like for contextual decision processes, you have a dependence upon the number of epochs already built in. times the number of actions. Right, so that's already kind of built into what we know is possible with reinforcement learning or with contextual bandits. So at a theory level, I think we're not losing. Now in practice, I think often there are shortcuts, and some of those are quite useful actually. So I think we'll discuss the shortcuts a little bit later. So that conceptually, I think this is what we want to think about. We want to think about solving the credit assignment problem at an individual step by saying we're using our learned policy to roll in, and then we're deviating, and then we're rolling out with our reference policy, right? And that gives us the cost for every action. And now that we have a cost for every action, we can train using a constitutive classifier to build a good policy. Okay, so that goes over and over again. Okay, so you generate an initial trajectory using your current policy. So that's what this might look like. And then for each decision on the trajectory, you have some observation. Here's your observation. You can look at the deviations. For each deviation, you can say, oh, I want to take that deviation, and then I want to roll out with my reference policy. And you can just keep doing this until you compute the final loss on each of the different trajectories. Okay, so so the key things here are sort of, you have a roll-in policy, you have a deviation, and then you have a roll-out policy. And we're mostly thinking about rolling in with a learned policy and rolling out with a reference policy. Okay, so generate examples, and then you update with those. Are there questions about this? Okay, so this is related to Yua's point. So the complexity, sample complexity of rolling out for all those different trajectories can be relatively large. And sometimes the loss functions have structure which allows you to shorten the rollout substantially, right? So in particular, if it's Hamming loss, for example, you don't really need to roll out that far. You only need to roll out one step, basically. All right, so one example is sequence labeling. You have some input, which is a sentence with the parts of speech. You want to make a sequence of predictions. Maybe you have a terrible predictor at the beginning. Everything is the determiner. And then you're going to pick some time step, and you're going to try all deviations from it. So you're going to say, oh, maybe at monster, I'm going to try determiner, noun, and verb. And then I'll use the reference policy to just fill things in. And then I'm going to compute the losses for each of these different trajectories. And I'll find that, see, this sequence here has no loss. This sequence has loss 2. This sequence has loss 2. Or no, loss 1, sorry. For Hamming loss.
Have to go all the way, right?
Yeah, in this case, we don't really have to go all the way. But we can still think about going all the way conceptually. So we're going to do something consistent with going all the way. Okay, so the losses are 1, 0, or 1. And then you can create an example based upon this. So it's just, oh, you have this word. The previous prediction was a determiner, and so forth. Okay, so another example is related to graph labeling. Maybe you want to label the nodes of a given graph, given various node features, graph node features. This is related to the WebKB web page labeling problem. So the node features could be the text on the web page, edge features could be the text and the hyperlinks and so forth. You can imagine throwing in arbitrary choices of features, whatever you might think is useful in the prediction problem. And then the question is, how do you actually, so we need to make a prediction on a graph. There's no natural sequence defined on that graph. So what we're going to do is something like what happens with leaf propagation, because we know that's a good information propagation structure. So you pick some starting node, and then you run breadth first search outwards. So you're going to go out and then in. So what does that look like? Let's see. That's not animated here. Okay. Okay, so these are kind of the examples. And now I think I'm going to, we're almost out of time, but I wanted to show you, right, so the second set of slides. Right, so why do we care about this? We care about this because it actually works pretty well in practice. So this is part of speech tagging, where all of the data sets have essentially the same features and the same representational complexity. So you're doing kind of linear predictors inside of things. And what you can see, so the x-axis is the training time, how long does it take to actually train? And the y-axis is the accuracy per word. So higher is better. So you want to be high and to the left, because that would mean no time, perfect accuracy. And what you can see is that, okay, so independent prediction is the black. You're just predicting for each thing independently, and that kind of suffers prediction performance-wise. And then you have a bunch of different methods for solving these problems related to structured support vector machine or structured perceptron or CRFs. Many of the CRF ones are remarkably slow. CRF SGD was something that Leon Batu worked on. Structured SVM is what Thorsten worked on. I think it ran out of RAM at some point here, which is why it didn't go beyond that.
Why is it giving so horrible performance?
What's that?
Why is structured SVM so bad?
I think it would give better performance if there was enough RAM available. The RAM ran out. Structured perceptron is something that Michael Collins worked on. So these are a bunch of approaches that I would say that nobody really considers these necessarily the state of the art, because people have gotten much more into representation learning recently. But we're trying to do a fair comparison. So we're keeping the same representation, the same sample complexity, and you kind of controlled experiments, right? And then you have kind of two variants of the structured learning that we're going on. Both of them are remarkably fast. One of them is using the exact same data set, and the other one is using kind of, so everything is kind of tuned to make CRF++ work well in terms of which adjacent words you use and whatnot. So CRF++ is optimized in the choice of what the context, what the window of features is. But you can also just optimize the window of features against this learning to search approach. And that's what the red line is. Okay, so in about a couple minutes, we can get a predictor which is quite good. All right, so I will show you the demonstration next time, but I wanted to show you this graph here, which I think is maybe even more convincing in some ways. So here we're trying to do, we're just measuring this computational speed of evaluation. And there are approaches based upon CRFs or structured support vector machines, and you can see that the learning to search approaches are dramatically faster, like 1 to 2 orders of magnitude faster at similar optimization levels, I would say, which means kind of C++ code written to be reasonably performant, but not necessarily super highly optimized as you might get if you talk to people at Intel. Yeah, are there questions about this? So is it clear why it's so much faster? So the thing which really makes this faster is there's a combination of you optimizing the global loss function, which gives you the good prediction performance, right? But it's locally decodable. So you're optimizing for local predictions, which gives you for the global loss function. So so this is just like in reinforcement learning when you're optimizing the policy for your long-term reward. And it's that combination of we're optimizing the global performance, global statistical performance, with a policy which does local predictions, which makes everything super, super fast at test time.
I mean, would you also say that the fact that you have this cost-sensitive classification implying that you have all the actions available, and so you can learn from, instead of like taking one action one by one, you have the reward for all the actions, and you can fit them much easier.
Say it again.
So you have like the cost for every action.
Yeah.
Which is way more information than had you just chosen one action and taken it.
Yes.
Because then what happens is like, I mean, you're constantly taking one action and you never observe the other actions. And or like the chance of like observing all of them is kind of low. Unless you have some like completely uniform random exploration policy.
Yeah, so there's certainly, there's a key thing going on here compared to vanilla reinforcement learning, which is we're starting out with a very powerful reference policy, which puts us into the neighborhood at least of a good solution. So that avoids a combinatorial blow up and how much exploration we might require to solve things well. Is that what you're referring to?
I was referring to something slightly different. I mean, what I was really saying is like you have the cost-sensitive classification, which provides which makes the learning much faster as opposed to having like a single action cost.
Compared to reinforcement learning.
Yeah.
Yeah. So one question is, what is the relative power of classification compared to contextual bandits? And it's essentially a factor of k in terms of the sample complexity.
K being the
number of actions. I think that in this setting, it's actually larger than that because it may be that you've made a bunch of mistakes in the past and that affects your global loss. But that may not be affecting the relative value of two actions right here. And so there's a trick, which I didn't really go into, when we are computing the costs, you actually subtract off the minimum cost. What you can do is you can observe all the costs.
Why would you do that?
It just kind of normalizes things. So this corresponds to what's called advantage learning and reinforcement learning. But because you know things precisely, it actually works better than advantage learning.
I should do that too.
Okay. So I believe we have spring break next week. Enjoy the break. Have fun. I'll see you guys the week after that. Talk to you later.
Yeah, actually, that's something that's worth trying. I mean.